Let's begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students again. I just pray that you help us to just collect our thoughts before the test. Just help us to glorify you, Lord, in what we do this day. You know, I pray, Lord Jesus. Amen. So, guys, I'll just tell you, and I've been working on putting the test together, and at the moment, I think it's probably too hard. Shock. Let's see here. I'm just flipping the last page again and again for effect, but let's see here. So, I gave you this list of proofs to do, right? And I think the structure I've settled on is I'm going to ask you to do 4 of those, actually. But the structure is going to be this. I give you a choice of, there's 4 that you get to pick 3 of, and then one of them is required. So you have a little bit of freedom, but not too much. I know you guys are short on time, so I will let the cat out of the bag and tell you that I'm not asking about the ML theorem, and I am not asking, the ML theorem is on the test, don't get me wrong, but the proof of the ML theorem is not on the test. And I don't think I asked you to prove the other one is this is also a significant reduction in studying the Cauchy's integral formula, m equals 0. That's not there either. That's significantly lightening your load, I think. So I will tell you that much, because I think you. Now, everything else there, I think, is still fair game. And the way it works is there are you choose your own adventure choose 3 of the 4. Those are worth, I think, probably 10 points apiece, and then the required one is worth 15 points. And the required one is harder. So, all right. So, and then the other problems at the moment, I don't know. I need to cut something out. I got a little bit too much right now, but I'm not sure what to cut. So I'll think about that. Maybe you guys got questions? Yes. Oh, before I forget. Michael. Well, anyway. Nathan, Peter, Josiah. These are just mission 5. I think Daniel's not done grading quiz 2 just yet. After I last left you, problem 7 ate hours of my time. Oh, that problem's evil. I chose problems from the book with answers in the back on purpose, right? Because I thought it would be friendly. Well, that one actually didn't have an answer in the back, did it? Did it? I can't remember. But anyway, what was your question? Before I waste more time?
It was a question on the proof of exact for the market. I don't know if you want to project it or what, but it was one line that I don't get. Maybe I am. You're not.
Yeah, you're right. Oh, it's working today. I'm sure it's not a mistake or a typo, because there are none of those in my notes.
I don't think it's
Okay, so. You just don't understand?
Panic button works so nice.
What's that?
Panic button is so nice. Oh, wait. Is it panic?
Yeah, we're going back and forth.
Oh, the Zoom button.
Oh no! Curses. Dang it. Now what do I do? Do I leave them? Should I stay? Should I go? I don't know.
Just saying, guys, they're videotaped very well.
Just looking at all kinds of inappropriate things here. All right, why did I plug that thing in? Where was it? Well, I guess I can't post this lecture.
Oh, my bad, guys.
Stop the video. Oh, no, leave it. Just leave it. It's fine.
I'll do that.
Just leave it. It's fine. Oh, I found a solution manuals for Gamelin, but it wasn't that helpful, by the way. Have you looked at it? It's some sort of consortium of Russian students that are trying to like just solve every problem in Gamelin and post a PDF on it. It's pretty hardcore, but I was looking at, well, I got it up, and look at this problem in particular. Look at this nonsense. Like they somehow, well, the solution to A is cool. That's nice. I like that. And B is fine. I figured that out. Great. But C, look at what they do in C. Look at this. Some of you already have, I think. What? What is this? This is nonsense. This square root is not a different square root at this one and this one. Both of these values output -5. Why on earth should you have different? Because they're both the square root of -5. How can the square root of -5 be different for different -5s? -5 is -5. How are they getting a minus here and a plus here? This is nonsense. Sorry. But I feel like that's what Gamelin wants us to do. They want us to get a different answer for C and D. All right, this is why I omitted 7, because I'm still upset about it and I can't overcome it. Why did I have this up? Close.
5 question marks.
Yeah. Oh, yeah. Yeah, that was not comforting to me either. I don't know. Maybe question mark for Russians is like, we won. I don't know. Like some cultures, like nodding one way is the opposite meaning or something. All right. I'm sorry. We only have so much time. I should stop wasting it. What happened here? Okay, so here we go. Stop that.
Do you guys want to go with the whole thing?
3.2 point what? Come on.
There are requests to go with the whole thing.
3.2 point what?
Point 10.
Point 10, okay. Well. All right. Sorry about number 7. Anyway, that will help your overall grades on your quiz, so I guess you'll be happy about it. But I don't know. I want my hours back. All right. So we're assuming this domain D is star-shaped, right? Which means we can meaningfully draw these little triangles inside there, right? Because that topological condition gives us line segments from the star center are contained in D. We're assuming that PDX plus QDY is closed in D, and we want to construct an H such that DH gives you back the form PDX plus QDY. So what do? We pick a star center, A, right? And we define H to be the integral along the line segment from A to Z of PDX plus QDY. That's well defined because the line segment has to lie in D, right? So what then?
You look at the triangle on the screen there.
Right. So let's see here. We go. So where's I can go back to. We just go through the whole thing. Is that it? All right. So I pick another point Z naught, right? A fixed point, right? Such that the line segment from A to Z naught's in D, and then I look at gamma 1. What's gamma 1 here? X equals to T for X naught to X, right? And Y equals to Y naught. So gamma 1 is this little red line segment, right? Green line segment, I'm sorry, right? You with me? The reason I'm going to do that is because that's going to allow me to explore the partial derivative of the function at z naught by x varying, right? And the red line segment is a little vertical line segment, and that will allow me to calculate the partial derivative of h with respect to y at the point z naught, right? So there is no, okay, let me go on. Let's see here. Any questions about this setup so far? All right. So we're going to then apply Green's theorem to the triangle T2, which is which one? If I could read my own words. Vertices A, Z naught, and X naught plus IY. A, Z naught, X naught plus IY. So it's this one, this triangle, right? Is that right? Yeah. So Green's theorem says that the integral of p dx plus q dy is equal to, over the boundary of the triangle, is equal to the integral over the interior of the triangle, and boundary, I suppose, of partial q partial x minus partial p partial y, but that's 0 because we're assuming that the form is closed, right? So we have, yes?
Does one of the vertices of the triangle have to be the star center?
Well, I mean, I guess you could look at triangles otherwise, but the reason I'm looking at that is because the star center is linked to the formula for h, so it's necessary to have that there, yeah. I mean, certainly we could look at other triangles, but I don't know if they would help us. Yeah? What is it? Sharon's just trying to stay awake. I'm not sure the meaning of her. Sharon's expression is look like a deer.
I'm learning about the theorem better.
Oh, okay. Let us continue the learning then. All right. Okay, so then what do we have? We have the integral along each line segment making up that triangle added together is 0, right? Because the integral over the boundary of the triangle is first leg plus second leg plus third leg, right? But we defined h of z to be this, right? So this is exactly h of z naught, or h of x naught comma y naught, right? And this is what? Well, if you, well, I guess it's nothing in particular just yet. But this over here, if you flip the entry, right? And so if I change if I reverse the pair, that's the reversal of the curve that brings out a minus in the line integral, right? Because if you reverse the curve, you get minus the line integral you started with. So that's why I have minus, this is h of x naught. That should be plus ty, I think. Yeah, unless I did something else, this should be x naught plus ty. Or, no. Oh. Is there an I missing there? I think that's the, let's think about this some more. Let's just draw the triangle again. So that's triangle, right? What are the points on the triangle? This doesn't need to be mysterious. This is x naught plus I y naught, right? What's this point? Oh, I'm sorry. This is what? I'm an idiot. This is A, right? This is x naught plus I y naught, right? This point up here is what? Yeah, x naught plus iy. So this is the line segment a to x naught. Let me just say a to z naught, okay? Then this one would be what? The line segment x naught plus I y naught, comma, x naught plus I y, right? And then this line segment here would be x naught plus I y, comma, a. Yeah, when I reformat these notes, I think I'd like to add that picture. Add this to the picture. It would make the proof better, right? Agree? So let's go back to the next page and see if we can understand better if there's a typo or not. It probably is. X, so I have a to z naught, which is this first line segment, right? Plus z naught to x naught plus ty. Oh, that's an I? Oh. Well, that makes more sense. Duh. Sorry. Oh, yeah. Okay, then it's fine. All right, phew. I sometimes don't trust the idiot who wrote these notes. Let's see here. And then, what's that? Family? Oh, Gamelin? No, Gamelin didn't. Gamelin cannot be blamed for this. If anything, I have ruined his exposition. Let's see here. So a, x naught plus iy to a. Okay, now it makes sense. The t is not a t, it's an I. Stupid font size. That's an I. Okay, now do we understand? So again, this is h of x naught, comma y naught, and this over here is h of minus h of x naught, comma y, right? Does that make sense? And then you have, why does this just leave you a q? Why is there just a q here? This one has what? Dx is equal to 0, right? Dy is equal to dt, or, well, dy. I mean, what about, yeah, dt. So the parameterization, I've converted it to a parametric integral of x naught. X is fixed at x naught, t dt, integral from y naught to y. Right. So you can differentiate that, or take the limit as, just differentiate it with respect to y, rather. And so what's this give us? This is 0, it's a constant, right? This gives us minus partial h partial y at x naught, comma y. And this, by the fundamental theorem of calculus part 1, gives me back q of x naught, comma y. When I differentiate this expression with respect to y, I get that.
So are you just not, for x the implication, are you just not specifying it the partial h and partial y at x naught, comma y?
And yeah, it is also at x naught, comma y. Yeah, I just omitted that. I probably, it would be better improvement to put that there also, yes. And then via a very similar argument, you could prove that partial h partial x is equal to p of x naught, p of x comma y naught. And again, similarly, right. But then, of course, as you take the limit as x and y go to x naught and y naught, you get that that dh is equal to p dx plus q dy at the point z naught. But z naught was arbitrary, so this proves that that the form p dx plus q dy is equal to dh on the whole star-shaped region. And that's the proof. Anyway, does that make sense? Yeah, if you can draw the triangle, right, you pretty much have this proof in the bag. I think that's the main thing. If you can't think of the triangle, if you don't think to pick a star center and to construct it, I mean, there's a couple of critical ingredients. The one is to construct H, right? The other is to look at the triangle. You put those two things together, everything else kind of falls in line, I think. Which is not to say this is an easy thing to prove on a test. I think it's it's not an easy question, but then again, I think you guys are smart enough to do it. So that's why I asked you. All right, any other questions then?
Could you go over number 6 on the quiz? Because I looked at your solution, but I didn't understand.
Uh-oh.
certain steps of it.
Does not sound good to me. Uh, you like problem 2? I think problem 2 actually is one of the exact. I think exact implies closed was one of the things on the. Is that one of the proof items? That was there.
Yeah.
All right, let's see here. So you said 6. Sorry, I'll get to it. I am trying to make sure that there's space on the test for one of those conformal mapping Laplace questions. So I should mention that. I know we haven't talked about it much in the review day, but don't extract too much from that. So which was the I think I more or less advocated Malia's solution, give or take an epsilon or something. But so what was the step?
Well, you say I don't see how you get that U of Z is in between A and B. Like, I know you do that on the next page, but you say you get a contradiction, but I don't see how you get a contradiction.
Let's see. So you agree that we must attain minimum and maximum values at, say, Z1 and Z2?
Right.
So that means that U of Z is between little m and big M, right? But we're also given that on the boundary, but that includes the boundary, right?
Right.
These bounds also hold to the boundary. So if, excuse me, what would happen if A was tighter than M, right? If A was over here, what would happen? Then the minimum violates it. I mean, we're given that A is less than or equal to U of Z for all Z on the boundary, right?
Right.
So, and the boundary, by the way, is I guess I do need that.
See, I think it's confusing because, like,
Well,
at least for some of your inequalities, you don't make it specific, like if it's on the boundary or if it's on D tilde, so it's kind of confusing.
Right. I'm not sure this is complete, actually, because, well, this is what I kept coming back to, but then I convinced myself this was right at some point, so I just left it. But I'm now not so convinced, because I think if I knew that Z1 and Z2 were actually on the boundary of D, right?
Right.
Then you'd agree with my argument that the A being larger than M would be a contradiction, because that would mean that there's something on the boundary, which is,
Yeah, that makes sense.
yeah. But what I don't know is that, what I'm not given from the extreme value theorem is that Z1 and Z2 are actually on the boundary of D. And maybe that's the rub.
Maybe.
So the proof I had before this that I think I may have given up on for other reasons, I forget, was either Z1 and Z2 are on the boundary or they're not. You know?
Mm-hmm.
So if they're not on the boundary, the boundary is also a compact curve, right? So there has to be some min and max that's attained on the boundary.
Yeah.
And how does that min or max have to stack up against U of Z1 and U of Z2? You could think about that. And maybe if we put those two things together, we can get it. I don't know. Maybe I need some kind of contradiction argument here or something. So
I don't know if it's correct, but I use the maximum principle.
yeah. Yeah, yeah. Yeah. Maybe. I mean, I'll have to think more about your solution. I'm not convinced that my solution here is correct, or at least there's something missing. I mean, I think that the result is true, but I'm not confident about my proof either. What did I say here? So you're just complaining that I still have a leap there in the follow-up.
Right.
This
and
paragraph
like
here.
Where you say it's true because of contradiction, I don't really see why your contradiction is a contradiction.
Yeah, I think that's only a contradiction if I know that Z1 and Z2 are on the
Boundary.
well. I don't know. I mean, see, I go back and forth. This holds for all D in Z naught, in Z in D tilde, right? So that means that also holds on the boundary, right?
Right. And so like if you apply that to A and B, when I was trying to work through your logic, you get the inequalities going the wrong direction.
Hmm.
Because if you put A there, you get A is less than or equal to U of Z2. not
Well,
U of
again,
Z2.
but maybe it's okay though, because if, I mean, this holds for all Z and D tilde, right? So it doesn't really matter, in some sense. I mean, it doesn't matter if Z1 and Z2 are on the boundary. We still have this inequality. So if there was, if if you could fit M in here, that would mean that there's some points on the boundary which violate this inequality. And that's the contradiction.
Isn't M equal to U of C1 though? Isn't that how you define that?
Yeah. I'm saying that if A was here, if you had U of Z1 was less than or equal to A, well, let's say less than A.
Oh, because it's U of Z is in between A and B on the boundary.
Right. I mean, because this,
Oh, okay.
that holds for
I think that
all,
makes sense.
it holds for all Z and D tilde.
Okay, that makes sense.
Okay, good. Because I was where you were at certain points in writing the solution, but I eventually overcame it and came to believe in the truth of this. But I admit, there's something about this problem in terms of thinking through it. I mean, so anyway, I will tell you, I did not put this particular one on the test this year. So you can breathe a sigh of relief. But there is a question about the maximum principle somewhere on the test, I'm pretty sure. So just not this one. Because I'm not currently satisfied with my ability to exude confidence about the solution of said problem.
Wait, so how is this
Uh-oh.
related to the maximum principle then? Like, you didn't use it.
Didn't I?
Where did you use it?
Oh, you're right, I didn't. Yeah, and see, that's the thing that, I know this is a maximum principle problem. That's a great point. This is a maximum principle problem, right?
Yeah.
I don't think I really use the maximum principle here, right?
Wait,
I
so
use the
did you-
extreme value theorem, which goes into the proof of the maximum theorem. So I think I don't think this is probably, the proof I'm giving here is probably not the correct proof for complex analysis.
Wait, so did you look at the proof I gave for this one yet?
I'm not, yeah, I share your, I don't know.
Because I like it in between the same thing.
I don't know. We'll
So I don't know.
see what the grader thinks. So, oh, other questions before I waste more time on, I mean, not waste, but spend more time on this. Yeah.
I don't know if you have a solution somewhere, but how would you
I will say this, that problem 7, this calculation was neat, wasn't it? That was neat how that worked out. But this is not some kind of hidden message, this is on the test. I'm just genuinely expressing, I thought that was a neat little calculation. That was the one redeeming aspect of that problem. So here, did you guys get these ones? I wonder if you noticed how close this was to being really complicated. See, if log is not holomorphic on the disk, you can't apply Cauchy's integral formula, right? You'd have to do something else, like actually calculate the integral in some sort of limiting. I don't know what you'd do. I honestly, I don't know quite how to solve this without a lot of thinking if the circle goes beyond and includes the point where the logarithm is not, it's not holomorphic. I don't know what, I'd have to understand that as some kind of sort of improper integral or something. Did you guys think through that, or did you just assume? Yeah.
I checked.
You checked, okay, yeah. It's very important to, before you apply Cauchy's integral formula, you should ask yourself the question, is the divergence actually in there? Is my integrand actually holomorphic? Now, if the integrand isn't actually holomorphic on the disk, then probably that means my question isn't well posed, since we don't really have other methods except for direct integration. And, I mean, we can integrate things which are not holomorphic on the on a curve, right? How would you do it? What if I was going to integrate, say, z plus z bar dz over the unit circle? I don't know. And say the circle radius 2. What you do, for lots of better ideas, I would just integrate from the definition, right? So this means what? So z is 2e to the it plus what? You just integrate that thing. What happens? You get what? It's not bad. And what is that? This is radius 2, right? So the area of this is what? 4 pi. So you see what this is? This is 2i times the area. Should that ring a bell? What just happened? Well, remember this piece integrates to 2i times the area. That was a homework problem you guys did. And this piece integrates to 0 because z is holomorphic, of course. So this is antiderivative 1/2 z squared. So I could have thrown this away at the start because it's a holomorphic function integrated around a loop. I mean, look for that. If I ask you to integrate a holomorphic function around a loop, right? If it's holomorphic inside the loop and near the loop, then the integral is 0, right? Cauchy's theorem. Can you prove Cauchy's theorem? Do you understand what was wrong about my proof of Cauchy's theorem when we did it the other day? Because none of you said anything to me, and what I said was total nonsense. I sent an email shortly after that. So let's see, I guess we have to do boundary of D, right? So the point is f equals to u plus iv is holomorphic on D. All right, and we also assume that f is smooth. just to keep it. I mean, all I really care about is the continuity of the first derivative, but let's just say f is smooth. I do that on a few, if I ask proof questions on the test, I mean, I do. And so I will at the start just say like P and Q or U and V is smooth. That's just to remove your worrying about the derivative being continuous. Like I'm not looking for you to say, by Morera's theorem, blah, 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 blah. No, no, no. We only have an hour. Yeah.
Would you be like prove Cauchy's theorem, or would you like give Cauchy's theorem and then say prove this? Or would you say English theorem, prove theorem 4.0?
I will definitely not refer to the theorems by number. That would be, I mean, there exist professors like that. Not here. Where was it?
I know someone who would be a professor like that.
Oh, there is a professor like that here?
No, I'm saying there's someone who would be a professor like that if he were to become a professor.
AJ?
No, Michael.
Oh, Michael.
Because like he's all about memorizing.
Oh, really? Oh, you mean the rack?
Yeah.
Okay. Let's see here. No, like if I was to, put the format of the questions, I state the theorem basically and say prove it. So, yeah, so if this was on the test, it would look something like, I give the necessary conditions. I would give the necessary conditions for D, which is what? It's a bounded domain. Basically, it's a domain for which Green's theorem applies, right? So I mean, if you look in the notes, I would cut and paste from the notes pretty much. So was this 4.3.2? I forget. So how's the proof of this go? Well, this is the integral of what? U dz plus, U plus I, U plus IV, dx plus I dy. This one I mean, this is not a necessary step. This is just because I'm trying to make sure I write it down right, okay? And so what I did in the class period that we talked about this is I, for some reason, wrote the derivative of f here. Why did I do that? That's not right. Why would we differentiate the integrand for no reason? But I did, and none of you called me on it, which is part of the reason I put these proofs on the test, because I feel like you're not following along. And so I need to do something about it. And this is what happened. Okay, so now you know. U dx minus v dy. It's disturbing to me if I feel like I'm the only person proving things in here. I mean, I go through the proofs. I want you to follow along. So that essentially is the definition, though, right? And then, so the boundary of D, right? And then I can apply the Cauchy-Riemann equation. Oh, no, I can't do that yet. Let's see here. How about now I apply Green's theorem. Now, D doesn't have to be simply connected. D can have holes in it. Green's theorem still applies, right? Green's theorem applies to bounded regions with holes. It's just understood that you have to integrate over the positively oriented boundary, which means that the outer edges are counterclockwise oriented, whereas the inner edges are clockwise oriented. But we don't have to get into all those details because they're all hidden in this step, which is wonderful. And so Green's theorem says what? I do minus Vx minus Uy dA plus I times integral. And we proved the complex Green theorem, so we have that to work with. Let's see here. So Qx is Ux minus Py is Vy actually here. So to get from here to here, I'm using Green's theorem, which was that integral of the boundary of D of Pdx plus Qdy is what? So in the first case, P is equal to U, and the Q is equal to minus V, right? In the second case, the P is equal to V, but the Q is equal to U. Now, I use Cauchy-Riemann equations.
In the email that you sent us, you said fractional Martin's standalone proof?
This is the standalone proof.
Really?
Yeah. There's a proof I have that's like 2 lines, which uses closed and harmonic form arguments.
You don't want to use that.
No, because unless you want to prove those other things in the test. I don't know. Some of those might already be on the test. I mean, I think this argument you can remember and keep with you for your, as long as you care to think about a complex analysis. It's pretty easy to remember this proof. I think this proof is very natural and easy. It's just Green's theorem and then apply Cauchy-Riemann equations, right? Now, since I differentiated in class, we ended up with second partial derivatives, and then I used Clairaut's theorem to argue that they had to commute. So we proved basically that if you have a holomorphic function, the integral of the derivative around a loop also is 0. That's the content of the proof we proved in theorem we proved in class. But I mean, why do you guys say anything? I mean, someone here must have known what I was doing was nonsense. Anyway, sorry. The other reason I asked these proofs is I've heard about the miraculous ability of the rack to memorize things, and I wanted to see it. I was told Michael can memorize large quantities of material. So essentially, like, one way you could study for this, of course, would be just to memorize everything without understanding is to regurgitate it back, which of course is not the spirit of the question that I'm asking you, right? I would like for you to understand the proofs in terms of a minimal set of things to remember. I mean, that's how I think it's best to try to prove things. Now, I personally had questions. I had some tests like this as an undergraduate where I was asked to be responsible to prove certain theorems, and I can still prove those theorems today because I was asked to do this. So I think it's a worthwhile exercise. So, anyway. So any questions?
So,
I do promise to put Cauchy integral formula question on test, or 2 at least. Yeah. Promise 2, at least 2. One of them might be a trap, though. Anyway, yes.
The existence of harmonic conjugate. To actually prove, like, I know there's the formula you get. So to actually prove that formula works as harmonic conjugate, would you have to use something like the triangle method we used for the closed on star shape?
Yeah, that's really a reasonable proof question if it is following the one we went through at the start of class today. In fact, you need another one too, right? You need the proof that
wasn't there the one about a certain form being closed if U is harmonic?
Right. You need that certain form is closed if U is harmonic, and then you also need the closed on star shape. Closed on star shape implies exact. So what you'd have the harmonic function implies that particular form is closed, but then by the theorem we proved at the start of today, that would prove that, applying the theorem we proved at the start of today, that would imply then that form is exact, and the V, I think, in that is the harmonic conjugate.
Right. So I understand that. How do you actually prove that's harmonic conjugate? Because you'd have to take second partial derivatives and then show that it's actually harmonic.
Let's see here. You have what was the form you have? U. Which one is the harmonic? Which is the closed form for U?
I think it's negative partial y u dx plus partial x u dy.
So you can show that this is closed, right? And then you get that this is exact, right? Let me call this omega. You get then that omega is exact by the theorem. All right, the one we went through at the start of class. But what does that mean? That means that dv is equal to omega. But what's that mean? That means that vx dx plus vy dy is equal to minus uy dx plus ux dy. What does that tell you? You can equate coefficients of dx, and you get vx is equal to minus uy, and you get that vy is equal to ux, which is to say that v is the harmonic conjugate of u.
How do you get that v is harmonic?
V satisfies the Cauchy-Riemann equations when paired with u.
Oh. Okay,
So
so
it's-
because it's part of a homomorphic function, you automatically.
Right. I mean, if you want, of course, we could directly prove it. So it's minus u. Let's see here, minus uxy plus what? Vyy would be uxy. I mean, if you don't want to quote a theorem, you could prove it directly too. But I think it's evident once you see that v is a solution to Cauchy-Riemann equations when paired with u, it should then be clear that u plus iv is a holomorphic function. Yeah. But you can see these are kind of a package deal, right? If I ask the triangle theorem, it's probably going to be the case that I also ask you to prove that harmonic form, that if u is harmonic, then that form is closed. And then a nice follow-up to that would be to prove that, what is it? Oh, that u has a harmonic conjugate on a star-shaped domain. It's a trifecta. There are other trifectas, right? Like the deriving the generalized Cauchy integral formulas. And I gave you the easy proof, right? The differentiate under the integral proof. You could improve what I did by doing induction, right? I just did the first couple steps. You could assume that it's true for k and show that k plus 1 follows. That'd be nice. I don't think the induction's that hard. It's no harder than the differentiation we did. And what would be a follow-up to that? What follows that? Well, how about Cauchy's estimate? And what follows Cauchy's estimate? What's the follow-up to Cauchy's estimate? Leibniz's theorem. That's right. There's another trifecta. I like to tell stories on tests, so yeah. Which is probably a bad thing to do, but it's it's what I do. Oh, I'm sorry, we're out of time. And I will post this so you can see my first page on the test if you must.
So you can study it